Today, we are going to continue our discussion of Thevenin and Norton equivalent circuits, but we are going to include dependent sources. All right, so let's consider the following circuit where we have a 20-volt source connected to a 6-ohm resistor connected to a dependent voltage source, which is providing a voltage of twice Ix. And let's say that we have an 8-ohm resistor here and a 10-ohm resistor here. So this will be terminal A, E, and let's say that our current Ix is the current that flows down through that 8-ohm resistor. So if I wanted to determine the quantity V Thevenin for this circuit, what would I need to do? I want V Thevenin as seen between terminals A and B. Let's say positive polarity reference on top. I literally just need to write V Thevenin with a positive polarity reference on top, then we solve for that quantity, right? So let me make a copy of this. Goodness gracious, what the heck did I just do? Sorry, having a little bit of a technical difficulty there, and also not entirely sure why it started me up on page 8, but that should be okay. All right, so might have been shorter to just redraw the circuit. Here we have our quantity VTH that we're trying to solve for. How might I go about solving for this quantity? Anybody? So, is it really mesh analysis if there's only one mesh? So Kirchhoff's voltage law could be used in combination with Ohm's law to determine that quantity Ix, the current flowing down through the 8-ohm resistor. And then let's say that we used KVL and Ohm's law to find Ix. How would we use that information to find VTH? Pardon? So there's actually two practical voltage sources, both of which contain the 6-ohm resistor. I don't have any problems whatsoever with us doing KVL and Ohm's law to get IX. That seems very reasonable. My question is, once we know IX, how can we use that piece of information to determine VThevenin? So you would be able to know the voltage drop over the 8 ohm resistor. And then Norman, I believe you said, and then the 10. Could you clarify what you mean by and then the 10? So the voltage drop over the 10 ohm resistor is 0. I agree with that. Could you elaborate as to why? And we talked about this a couple of times in the last class. Exactly right. There's no current flowing through the 10 ohm resistor, which means there can be no voltage drop over the 10 ohm resistor. So in reality, the Thevenin voltage in this circuit represents the voltage drop over the 8 ohm resistor. Okay. So let's take the method that was suggested, simply applying Kirchhoff's voltage law around this loop, solve for the quantity Ix, multiply that by 8, and we have VTH. So we would have negative 20 volts plus 6 ohms times Ix minus 2 Ix plus 8 ohms times Ix is equal to 0. So that's going to look like 6 minus 2, which is 4 plus 8, 12 Ix is equal to 20 volts. And from that, over 12 ohms, which is going to be 5/3 of an amp. Divide both by 4, right? Yeah, 5/3 of an amp. And from that, VThevenin is simply 8 ohms times Ix, or 40/3 of a volt. Anything seem unreasonable about that analysis? All right. So I'm going to copy our original circuit down again. Hopefully without as many technical difficulties this time. Now let's talk about how we would determine our Norton current. McKinley, could you give me a refresher on what our process should be, if you recall? If not, I'll pick on somebody else. Right. So not the resistance, the Norton current. So the Norton resistance and the Thevenin resistance are defined in the same way. Carter, were you scratching your head or raising your hand? Short circuit A and B. And then we measure the current in the short circuit. And because we found the Thevenin voltage with the positive polarity on top, our Norton current should be directed down. So, Brittany, I haven't seen you in a while, so I'll pick on you. What circuit analysis method would you care for us to use to determine the quantity I Norton in this circuit? Okay. I personally would have chosen mesh, but no. The reason why I would have chosen mesh is twofold. There are 2 meshes in this circuit, so it's a 2-equation, 2 unknown system. With regards to nodal analysis, I have the node at the top of the 20-volt source, the node between the 6 ohm and the 2 Ix source, so that's 2. The node between the 2 Ix and the 10, so that's 3. And then the bottom node. So yeah, I guess it's going to be a 2-equation, 2 unknown system either way. I would have chosen mesh analysis because I'm looking for a current, but we can easily do nodal analysis here and get it as well. So that's what you suggested. That's what we're going to do. Okay. So which node would you choose to be our reference node? All right. Okay. We could have done it this way. It would have been a little weird, but that'll be all right. That's the wonderful and sometimes terrifying things about nodal analysis and mesh analysis. We can really choose our reference to be wherever the heck we want it to be. It's just some things are a little bit easier than others. I would agree that the bottom node here is probably the easiest way to do nodal analysis. Although we will have to write a supernode equation because we didn't choose a node, didn't choose a node as the reference that was tied to our voltage source. So I'm going to call this guy VA, this guy VB, and this guy VC. And obviously, because the right-hand leg of the 10 ohm resistor is shorted to the bottom, the right hand and all of the bottom are our reference node. So I only have those 3 nodes to worry about, right? Because I have 2 voltage sources, I'm going to have 2 voltage relationship equations. Nick, would you mind helping me out with those voltage relationship equations? So let's start with the 20 volt source. How does the 20 volt source relate to our nodal voltages? Equal to VA, absolutely right. And then we have our 2IX voltage source. How does it relate to our nodal voltages? VC minus VB, absolutely correct, thank you. We have a controlling variable equation since we have a dependent source. So I'll put that guy over here. So I need to express IX, the current flowing down through my 8 ohm resistor, in terms of my nodal voltages. Mo, how would I do that? VC over 8, that's it. All righty, and now I need to write my KVL equations here. So since the supernode that has my 20 volt source is between node for that one, so I'm only going to have a KCL at supernode BC. So because it's been a minute since we've done anything involving a supernode, what I'm going to do here is I'm going to just try to draw a little bit of a loop around our supernode, and not that. We're going to find this current, and this current, because those are the 3 currents leaving our supernode. Bradley, what is the current directed to the left through our 6 ohm resistor in terms of our nodal voltage quantities? VB minus 20 volts over 6 ohms. Okay, that's a perfectly reasonable way to do it. And the current flowing down through the 8 ohm resistor. Exactly right. And the current flowing to the right through the 10 ohm resistor. VC over 10 ohms. Thank you so much. So that is correct. So we can use this guy, this guy, and this guy to solve our 3 equation, 3 unknown system, or we could do a substitution where we substitute in IX is equal to VC over 8 ohms to make it 2 equations, 2 unknowns. Whatever floats your boat, let's just solve for those 3 quantities. So we know that VA is 20 volts. We don't know what VB is. We don't know what VC is as of yet. We don't know what IX is. So I have -1 VB, 1 VC, -2 IX is equal to 0. And I have 0 VB, 1/8 VC, -1 IX is equal to 0. And then I have 1/6 plus 1/8 plus, excuse me, 1/8 plus 1/10. And then positive no IX, positive 20/6. So I got 7.143. $9.524 and 1.190 ampere. Now, again, using a calculator I'm less comfortable with in my TI. So there's always a possibility I entered something in wrong. I see a couple of thumbs up, so I believe I did it correct. So, assuming that these 4 values for VA, VB, VC, and IX are correct, Dylan, could you tell me how I can use those values to determine the quantity I Norton? Right, so if I'm trying to find I Norton, so let's talk about, because we chose to use nodal analysis, how we could use those nodal analysis results to find I Norton, okay? So I would argue that the current that's flowing through the 10 ohm resistor is the exact same thing as the Norton current that's flowing down through the short, because they're effectively connected in series, right? So how do I get that current through the 10 ohm resistor? That's it. That's absolutely correct. I Norton would be VC. Would simply be VC over 10 ohms, which should look like 0.952 amps. If I moved my decimal place 1 point to the left correctly, which I feel relatively strongly that I did. Bradley.
I wanted to ask if we could go through that with mesh analysis as well.
Sure. So, yeah, doing mesh analysis, I'm going to try to tuck that mesh analysis in just right here. It's not going to be overtly large, I don't think. So we would have a mesh current, I'm going to call it IA, and a mesh current IB, right? We have a controlling variable. And to save myself a little room, since I put myself in a bit of a box here, we could say that IX, Bradley, what do you think our controlling variable equation for IX should be? So it should just be IA minus IB. So let me explain why. IX is obviously a current. IA minus IB is obviously a current. If I multiplied IA minus IB times 8 ohms, what I would be getting is the voltage drop over the 8 ohm resistor, which isn't exactly what we're looking for. We were looking for the current. All right, so that's one equation taken care of. Then I would need to just write a KCL equation for mesh, excuse me, a KVL equation for mesh A and a KVL equation for mesh B, and I'd be finished. So KVL at A would be -20 plus 6 ohms IA minus twice IX plus 8 ohms IA minus IB is equal to 0. And then I would have a KVL around mesh B. That would simply be 8 ohms IB minus IA plus 10 ohms IB is equal to 0. We could solve this system and you should find, so it's 3 equations, 3 unknowns, including the quantity IX. You should find obviously that our IXs are the same, and you would find that I Norton would be the mesh current IB in this case. So if you want to take a minute or two to do that to verify it, by all means go ahead. Either way is an equally valid method of determining the Norton current for this circuit. Mm-hmm. All right, so we have found V Thevenin. I'm going to go up here. There, we found it. We have found I Norton. So my next question is, how do we find R Thevenin? V Thevenin over I Norton. That is a perfectly reasonable way to do it. Okay, I'm going to tuck that in right here. R Thevenin. If my stylus will write, there we go. V Thevenin over I Norton, which is 40/3 divided by 0.9524. So I get 13.9997. So I feel 14 ohms is a reasonable thing to assume it is, with the understanding that there may be a little bit of rounding error in there because I definitely truncated the value of I Norton. Okay, great. Okay, so we have determined, and I'll put a box around this. That R Thevenin is 14 ohms. So my next question becomes, how can we check this answer? Okay. And so what I mean by that is we need to develop a method by which to determine the Thevenin equivalent resistance of a network that contains a dependent source. All right. So I'm going to scroll to the next page here, and I'm going to recopy down my circuit. I'll give you guys a moment to catch up with me, as it were. And then we're going to talk about this process. So who remembers what the rules are for determining the Thevenin or Norton equivalent resistance of a circuit? Has to be a dead network. So what do we do to make this a dead network, Connor? Make the 20-volt source a wire. We don't do anything to the dependent source. Okay? So for a dead network, that means that all of our independent sources are turned off. All of our dependent sources will always be on. Okay. So dead network means only independent sources are turned off. So that creates a little bit of a conundrum. Okay. Because we are being asked to look into these open circuit terminals and determine what our Thevenin resistance is. And the problem is that we can see that there's a 10 ohm resistor, and we can see that there's an 8 ohm resistor, but in parallel with that 8 ohm resistor, there is a 6 ohm resistor in series with a dependent source. So as it turns out, it's not going to be as trivial as resistor combinations in this case, okay? What we're actually going to have to do is to go back and fundamentally apply where Ohm's law originated from, okay? So what I mean by that is several weeks ago, we observed that for a linear black box network, if we took what I'm going to call, if we applied a voltage source to a linear black box network and we measured a voltage, which I'm going to call V test, across the terminals of the black box network, and we measured a current, which I'm going to call I test, flowing into the black box network, we found that the resistance of the network was simply the ratio of V test divided by I test. Ohm's law. We could do something very similar, where instead of applying a voltage source, we could instead apply a current source, S, and determine those same two quantities. So we have our same black box network. We found the voltage drop across the terminals. We test the current flowing into the network. I test. We observe that the resistance of our material or network under test is simply V test over I test. So we are going to use our knowledge of Ohm's law and its fundamental derivation to apply what's called a test source method for determining the equivalent resistance of that circuit, that dead network containing a dependent source, okay? So what I mean by that is that we can take that network at the top and we can apply either a voltage source across the open circuit terminals. And that voltage can have literally any value that we want or any polarity that we want. And the ratio of V test that we choose divided by I test that we measure will be the Thevenin resistance of the circuit because it's a linear circuit. Or we could apply a test current source having any value in any direction. And any voltage V test we measure will give us the Thevenin equivalent resistance by simply dividing that measured test voltage V test divided by our applied test current I test. Okay. So either of those methods will work. So I want to prove it with both of them. So I'm going to take this guy right here. I'm going to come down here, paste it in. And I'm going to let you choose. Okay. So the first thing that I'm going to allow you guys to choose is whether we're going to use a voltage source. We have a binary decision, literally just pick voltage or current. Voltage, okay. Abigail, I would like for you to pick the polarity of the voltage source. So positive polarity on top or negative polarity on top? Positive on top. All right. Your name is Haley, correct? Haley, what should the magnitude of our voltage source be? Literally just pick a number that sounds reasonable. Pardon?
20.
20. All right. We're using a test voltage of 20 volts. Okay. The number that we choose and the polarity that we choose is inconsequential. So you can use literally whatever you feel like and it'll work out correct as long as you're doing the circuit analysis correctly. So the quantity that we're trying to find is this current I test leaving the positive polarity terminal of our test voltage source. Okay. So, Joel, haven't talked to you in a bit. What method do you want to use to determine that test current I test? Mesh, okay. Seems perfectly reasonable. Let's call this guy mesh current IA. Let's call this guy mesh current IB. We have a controlling variable. So Hayden, how am I going to express IX, the current flowing down through the 8 ohm resistor, in terms of our mesh currents IA and IB? Exactly correct. Now I can just write my two Kirchhoff's voltage law equations around these two meshes. So, wonderful, thank you. And now we'll do KVL at mesh B. And Harold, would you mind helping me out? All right, so we have three equations, three unknowns. Let's solve this system for IA, IB, and IX. And then once we know those results, let's find I test and R7. So first, solve our system for IA, IB, and IX. So we have 1, -1, -1, 0. 6 plus 8 is 14. -8, -2 is equal to 0. And then we have -8, +18, 0, -20. I believe. So I get -0.714 amps, -1.429 amps. IX, I get to be positive 0.714 amps. Anybody else get those numbers? Let's start there. Okay, people are nodding their heads in agreement. So, David, B and IX, what should I test be? So I test is the current that's leaving the positive polarity terminal of the 20-volt source. And IB is the current that's entering the positive polarity terminal of the 20-volt source. So I would argue that we can see that I test is just negative IB. Does that make sense? So we will get 1.429 amps, 10/7. So R Thevenin is our test voltage, 20 volts, which we chose, divided by 1.429 amps. So that's going to be 20 divided by 10/7. Is exactly 14 ohms, which is the result that we got taking the Thevenin voltage and dividing it by the Norton current that we calculated several minutes ago at this point. Okay. So our test voltage method obviously returns the correct answer. So let's take a moment now to effectively rework this portion using a test current source so that I can illustrate how you go about using that and prove that it's going to give us the same thing. Colby, what's up?
So we could have picked any number other than 20 and it would still give us the same.
Exactly right. And it's because our circuit is linear, we've proven that the excitation scales, right? The homogeneity factor. So with a 20 volt source, I got a current of a test current of 1.429 amps. So if I had chosen a 40 volt source, that doubling the voltage, that current should have also doubled, but that ratio is going to be a constant because it's a linear circuit. So I tend to just simply choose 1 volt sources and 1 amp current sources because it doesn't really matter what number I choose. But 20 volts works. You want to introduce a whole bunch of rounding error, go for it. It should all be okay. So the value, so the magnitude of our test voltage does not matter, and the polarity of our test voltage does not matter, as long as we measure our test current leaving the positive polarity terminal. Excuse me. All right. So I'm going to copy down my circuit again. For whatever reason, it showed up way down here this time. And now we're going to apply a test current source. That's literally our only other option. So Kennedy, do you want our current source to be direction up or direction down? Down, okay. And Mitchell, what value of current do you want us to use? 5. All right, so we'll have 5 amps direction down. So that means that we are trying to solve for this quantity V test, positive polarity on bottom, okay? So the positive polarity of our test voltage should be associated with the head of the arrow. And so effectively, this is forcing the current to flow out of the positive polarity terminal, which is the exact same situation we had a moment ago. Okay. All right, Oren, what method of analysis would you care to use? Mesh, okay. Let's call this guy IA. Let's call this guy IB. So we obviously have a current source in our circuit. So now we're going to have a current relationship equation. So Henry, could you please tell me how the 5 amp source relates to our mesh currents? So the 5 amp source says that the current flowing through the rightmost branch of the circuit is 5 amps direction down, right? That's what that source literally forces to happen. So if we look at mesh current IB as it flows along its clockwise path, when it reaches that right-hand branch, it is also flowing down. So that means that IB is exactly equal to 5 amps. Does that make sense? We have a controlling variable. I think at this point, this is the 3rd time we're doing this, so I'm just going to go ahead and say that obviously IX is equal to IA minus IB. like it has been the previous 2 times that we've done it. So where's my third equation going to come from? Anybody? Yeah, so KVL equation around mesh A. So, Skylar, help me out with our KVL at mesh A equation, please, ma'am. I'm just going to leave it as IX because I'm lazy. That'll work too. Yeah, so 8 ohms times IX. So we would have so I personally would have called that particular version of IX IA minus IB, but I understand it absolutely doesn't matter. We have 3 equations, 3 unknowns. So let's take a moment to solve for these guys. So IA, IB, and IX, we should see that we get different values than we did in our last analysis. So for my first equation, I have 0 IA, 1 IB, 0 IX, 5 is my constant. In my second equation, I have 1 IA, negative 1 IB, negative 1 IX, 0 is my constant. And in my third equation, I have 6 IA, and then negative 2 plus 8 is positive 6 IX, 0 is my constant. And I happened to get 2.5 amps for IA, 5 amps for IB, and so negative 2.5 amps for IX. Anybody else get those results? Everything seem okay? Anybody? All right, so we'll find out very shortly if those results are correct, since nobody seems to be confirming anything. By the way, if I get something wrong, by all means tell me. I'd rather fix it. All right, so we know those 2 mesh currents, and we know the quantity IX. So my question is, how do we determine V test now that we know those quantities? Bradley.
Would V test be 10 ohms times I test plus 8 ohms times IF?
Not quite, but very close. So your idea there is perfect. We can do a simple Kirchhoff's voltage law loop where we have V test and then the voltage drop over the 10 ohm resistor and the voltage drop over the 8 ohm resistor, and those 3 things are going to be related. But we need to be specific about the polarities over which we define our voltages, right? So your suggestion was like this. So that's V10, and that's V8. And so if we did KVL around that loop, we'd have negative V8 minus V10 minus V test is equal to 0, which we can rearrange to find V test is equal to negative V8, which we know to just be 8 ohms times IX, and V10 is just negative IB times 10. Right, so 10 ohms times IB. Or I've distributed the negative sign out at the front. And so that's going to be negative eight times negative 2.5 plus 10 times positive 5. Did I do that? Let me make sure I got all my signs right here. So when I move V test to the other side, I'm going to have negative V8 minus V10. Right? Is my algebra correct there? Let's start there. Okay. But IB is a positive quantity, right? So there we go. Yeah, no, you're right there. Okay. Yeah, I missed it. So I want to be. All right, so V8 is 8IX. V10 is 10 times the negative IB. Okay, I'm just trying to make sure I have the right number of negative signs and everything in place there. All right, so if we substitute in our numbers here, negative 8 times negative 2.5 minus 10 times negative 5 gives us 70 volts positive. And then from this, R Thevenin is V test, the 70 volts that we determined, divided by I test, the 5 amps we chose, which should turn out to be 14 ohms yet again. Thank you for helping me find that negative sign. So, test source methods generate the exact same value as simply taking the Thevenin voltage and dividing it by the Norton current. Okay. The reason why this is important is because you may be asked to find the Thevenin resistance of a network that doesn't contain any independent sources. And the only way to do that is to use a test source method. Because if there is no independent sources in a system, you can't determine a Thevenin voltage or a Norton current because there's nothing exciting it. So effectively, you're going to get an indeterminate 0 over 0. So I believe on the in-class assignment that I give you guys, the first problem I ask you to work, it does have independent sources. So probably the most easy and logical way to determine the Thevenin resistance is taking V Thevenin divided by I Norton. But for the second problem, I believe you don't have an option. You have to apply a test source method to it. And on exam 2, I will absolutely give you a problem that necessitates the use of a test source method to solve it. All right, so that's Thevenin and Norton equivalent circuits. In-class assignment time.